Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is lecture 18. Today we're going to talk about exponential random variables. But I want to give you a better sense of the answers to a few questions. Where do these come from? Which you could continue into where is this going and what is it doing right now? In order to answer this question, we're actually going to be brought to a slightly more advanced application topic, which is that of Poisson Point Processes. So that's going to kind of be the answer to this question of where these exponential random variables come from. We're also going to see here an illustration of something I like to call the CDF trick. And then finally, we'll end with an introduction to the gamma distributions, which is a whole family of continuous random variables that include the exponential random variable as a special case. All right, so let's get into it here. As a reminder, you want to think of the exponential random variable as a continuous analog of the geometric random variable. So the exponential random variable, and remember this is dictated by the PDF that f of, let's say, t is equal to lambda e to the minus lambda t for t greater than or equal to 0. And here we're just thinking of a situation where, generally speaking, this models the amount of time that passes. And so that's why I'm using t here instead of x. But again, you could use x, it doesn't really matter. Is the continuous analog, or I should say continuous time analog of the geometric random variable. Remember that the geometric random variable asked, let me try something enough times, and what's the time of the first success? So this is the try number of first success. All right. The geometric random variable handles questions such as, how many flips do I need to do before I get my first heads? So this handles questions like, how many flips before my first heads? And notice here, we're just looking for the first instance of something. Whereas with binomial, we're trying to count several. The exponential, by contrast, answers questions like, so analogous questions include one, how long do I need to wait at the DMV, before being served? Or, for example, how long do I need to remain on hold before speaking to, let's say, an agent or representative? Or or 3, for example, would be, again, pertinent to the times that we live in. How long do I need to wait before it is safe to touch something that I think might have the virus that causes the novel COVID-19. So this is SARS-CoV-2. And just to sort of highlight the general categories, and I want you to think of these as keywords to look for whenever reading a problem, which should ideally prompt you to use the exponential random variable. Is you want to think of this as being the subject of queues. Here we could think of these as calls or emails nowadays. Or alternatively, we could think of any sort of deterioration process. Deterioration. Or decay, such as in radioactive decay. So these are the types of processes that we model using an exponential random variable. And you'll notice that in every one of these instances, the question is not, let's say, how many, but rather how long, which indicates a continuously varying time. And thus why we're using continuous random variables. All right, so as I already mentioned up here, the PDF for an exponential random variable is something that looks like this. So it's lambda times e to the minus lambda t for t greater than or equal to 0, and it's 0 otherwise. I want to also give you a few clues for what to look for when being given a word problem, so that you know what's the first step you need to take after you've recognized, I think I need to use an exponential. Now, how do I go about in identifying the parameter which governs this distribution, which is lambda? All right, so the first question. All right, so you know you need to use some exponential random variable, which is again governed by this parameter lambda. Now what this means is that if you're trying to answer the question, what's the probability that my time lies in a certain range? Well, this is equal to the integral from a to b of this lambda e to the minus lambda t dt, assuming both a and b are greater than or equal to 0. So again, to solve the problem, you're going to need to find lambda. So how to find lambda? That's what you're going to need to do in order to really get running with the problem. From experience, I see there are two main forms. So the first form is that you're given the average amount of time. So the average amount of time is given. In other words, what that's telling you is the expectation of t. And you'll recall, and in our homework, we're deriving that the expectation of an exponential random variable is 1 over lambda. So once you have that, so let's say that's your average, then you can automatically compute that lambda is just 1 over the average. And you're done. You can now just continue with straight up integration and call it a day. The second common way in which exponential random variables are presented in word problems is you're given what's called the half-life, which is synonymous with the median here. So you're given half-life is given. So you want to think of this half-life as something that usually happens in this problems that talk about the third category, which was deterioration and decay. Half-life is the same thing as the median, which sometimes people like to call T1 half. And the formula for T1 half as it relates to lambda is that it's the natural log of 2 divided by lambda. So in particular, if you know the half-life, then you can just solve for lambda by saying take natural log of 2 and divide by whatever this half-life time is, T1 half. So unless you're given lambda directly, and sometimes you will have problems where that is given directly, more often than not, you'll find the major step to successfully solving the problem is using one of these two pieces of information to determine lambda. Let's go ahead and look at an example where we do the second one. Last lecture, we addressed this average amount of time version. So let's go look at an example where this occurs. So here's an example, and this is actually based on real data. So there was a report in April 2020 where some scientists basically measured what is the half-life of an individual coronavirus, which, you know, again is a tiny molecule. It's not really a molecule. Actually it's a huge collection of molecules with, you know, RNA and all sorts of things in there. It's not quite a cell, but, you know, it's something that's on the order of that size. Just to, you know, give you an idea of the relative scale of a single coronavirus molecule, and you know, again, it's something that kind of looks like, you know, it's got all these spike proteins on it. If an oxygen molecule, you know, O2, or you can think of a carbon dioxide molecule. So then you've got, you know, another carbon, CO2. If this were the size of a person, then a coronavirus, a single coronavirus would be something like a little bit taller, in fact, than the Empire State Building. All right, sorry, this is a really bad Empire State Building. This is our SARS COVID-2. So basically the relative scale of a single carbon dioxide molecule to a coronavirus is like me standing next to the Empire State Building. It's actually between the Empire State Building and the actual tallest building in the world, which is the Burj Khalifa. Anyhow, they did some studies and they asked, well, how long does a single coronavirus live on plastic? So, you know, you think about maybe a delivery driver or something has it on a plastic bag. What's the half-life of a single coronavirus on a plastic surface? So on a plastic surface, has a half-life of 6.8 hours. Let's just go ahead and round up and call that 7 hours to make our computations a little bit easier. Now, what this means is that the probability of whatever, bombarded by a little radiation, which just comes from the sun and things like this, deteriorating that single coronavirus, the probability of it lasting more than 7 hours on a plastic surface is is 50%. That's what this whole median notion is, 50% above and 50% below. Because it's continuous, this actually specifies a unique moment in time. So let's imagine we've got a plastic bag, and it has 1,024 coronaviruses on its surface. So a plastic bag has 1,024. I chose that number because it's 2 to the 10th. Has 1,024 SARS-CoV-2 units on it. What's the amount of time required for all but one coronavirus to basically break apart and dissolve and no longer be infectious? For this, again, is kind of on average, all but one coronavirus to decay. All right, so we know each one of these coronavirus things with all the spikes on it is subject to just break apart randomly, and that's just because of all the various influences there are in the world, oxygen and other corrosive molecules. But let's imagine I got about 1,000 of these guys, and each one is like decaying with some probability. And that probability is actually well governed using this exponential random variable. And I know that the chance of any one molecule lasting more than 7 hours is less than 50%. So now I want to ask, well, how much time do I need to let elapse where I can expect all but one coronavirus to have basically just fallen apart? We can do this calculation by using sort of a combination of binomial thinking and exponential thinking. Let's go ahead and see how that works. So the bottom idea is that we want little p, which is the probability that a coronavirus lives longer than t. We want this p to be such that when I multiply this out, this probability across each instance here, because I'm looking at basically a bunch of independent coronaviruses, I want this NP to equal 1, where N is 1,024. That's because we want to think of this as basically a collection of yes or no's, but where the probability of that yes is a function of time. Yes, it's lasted longer than t, or no, it hasn't lasted longer than t. P will be the probability that it's lasted longer than t, which you can think of as this xi, which sort of turns on, says that this guy's on. All right, so this is basically the binomial expectation. P, a function of time. All right, well, luckily we can just now solve this. We want the probability of an individual coronavirus surviving to be 1 over 1,024, because then when I multiply this across the 1,024, the expectation will be that only one has survived. So now I just need to plug this in. So I now have 1 over 1024, which is the same thing as 2 to the minus 10th. It's the same thing as saying that the probability of the lifetime of this coronavirus being greater than t, which is the same thing as integrating from t to infinity. And I'll just use a little dummy variable, lambda e to the minus lambda s ds, which if you recall is the same thing as e to the minus lambda t once I've canceled out the thing that goes to 0. I want this to equal, I want this to now equal this. We call this sometimes the survival function. But anyhow, we're now left to a situation where we now solve 2 to the minus 10 equals e to the minus lambda t. Now, if we remember, half-life is 7 hours. So this means that lambda equals 1 over 7 times the natural log of 2. Because, if we just go back over here, we divide by t1 half. t1 half is 7 hours. So I'm just going to keep that out front because it's going to make it look a little more suggestive. All right. So what this then gives us is you want 2 to the minus 10 to equal e to the minus t over 7 natural log of 2. If I take the natural log of both sides, then I'm going to end up with something that looks like this. Natural log of 2 to the minus 10, which is the same thing as minus 10 times natural log of 2, has to equal minus t over 7 times the natural log of 2. All right, so that's this side. Take natural log. And what I have written over here was just taking the natural log of the other side. And so just by matching coefficients of natural log of 2, I can see that, t needs to be 70. So what that means is that the probability of an individual coronavirus surviving after 70 hours is 1 out of 1,024. So that in particular, if I have a 1,024 coronaviruses, then if I ask what's the expected number, it's just 1. Now I can ask a related question. So here's sort of a part B example. Now, what's the probability that after 70 hours, no coronaviruses exist? This again is out of that 1,024. Well, we just determined that the probability of surviving of that extremely destructive virus, SARS-CoV-2, SARS coronavirus 2, beyond 1,000, beyond 70 hours is equal to 1 out of 1024. So that means by the law of complements, probability that it doesn't survive is 1 minus this. So now I just need to treat each of my coronaviruses as independent. And now I would need to just ask, well, I want each of these to die, at least at that 70-hour mark. So probability all 1024 viruses die. One minus 1 over 1024 raised to the 1024. Well, remember, I can approximate this using 1 minus x is approximately e to the minus x. So this is the same thing as e to the minus 1 over 1024 raised to the 1024, which is equal to e to the minus 1. And this works out to be roughly 36.79%. It's 1 over e is 36.79%. And remember, what we've got here is basically a binomial with n equals 1024, p equals 1 over 1024, and k equals 0. And what I'm writing over here is exactly the Poisson approximation at k equals 0, but where lambda equals n times p, which is 1. So this is where lambda equals 1. And so we're actually seeing our old friends of the binomial and the Poisson appearing in this sort of back of the envelope calculation. Now, this sort of coincidence of exponential and binomial and Poisson actually is a pretty prominent theme in what we're going to talk about today. One, in justifying why is the exponential random variable like the right thing to look at, and two, how do we model more generally processes that sort of seem to occur randomly in time. And this is very useful subject to study if, say, you're owning a business and you want to estimate the arrival of customers. This is all governed by what's called a Poisson point process. So let's dig down and understand where these Poisson point processes come from. And this really gets at the answering the question of where does the exponential random variable come from? All right, so here we're going to talk about Poisson point processes. And remember, Poisson stands for fish. And so we've got all these little happy fish. They're happy to get some recognition. But additionally, this is the answer to why does this exponential random variable model so many things? So this process of understanding where this model comes from really is something that people like physicists are really good at doing. You sort of try to figure out, how do I compute a thing? And you're going to make all these simplifying assumptions. But at the end of the day, all those simplifying assumptions actually end up being like correct, or at least very useful. So let's try to understand where the exponential random variable comes from. And this is going to kind of get at the question of what is the time of the first arrival of a customer. All right, so here's our concrete question. What is the probability distribution for the time of arrival of the first customer. So that's going to be our concrete question. So one of the important things to first get at is understanding, well, let's say I look at my day and I ask, well, what is the average number of customers that arrive in a day? All right, so, and I'm gonna try to be a little more general. I'll just use, let's say we have some time window. So this is 0, and this is some time t. You might think of this time 0 as when you open. And suppose we know that the average number of arrivals in this window of time, 0 to t, is lambda. All right, it's just notation, but we're going to see why that comes up. So let's imagine I subdivide. So let's subdivide 0 to t into n little slices. And so I want to think of this as, if this is t over n, this should be our first slice, and then we're looking at 2t over n, and so on and so forth, so that I subdivided so fine that you're only going to count whether or not there was an arrival in that window of time or not. And we're doing that so that we can get at what's the number of customers into n little slices, where n is such that only one person could arrive in a slice of time that looks like, t times I over n to t times, let's say, I plus 1 over n. In this window. So you can imagine that we're slicing in so that this order of time looks more like seconds. So, n could be your number of seconds in 0 to t, e.g. So that's an example. And it's unlikely that two customers are going to arrive at exactly the same second. So let's first estimate the probability that there are no arrivals in this window of time. The reason why we're doing this is we can then define xi to be 1 if an arrival occurs in t times I over n, t times I plus 1 over n, and 0 if no arrival occurs. This is getting at that the number of customers that will arrive in my window of time t, I can think of as just the sum of these IID random variables, Bernoulli's. So this actually ends up looking like a binomial. So let's first of all figure out what is the probability of such an arrival. So the probability of arrival of a customer Well, I need to take that if the average number of arrivals is lambda in that window of time, then I need to effectively take lambda and then just divide by t over n, or n over t. So let me just write it like this. Yeah, because we need n to be much larger than t, so that this is this works out here. This kind of makes sense just because the number of windows that I'm dividing this into corresponds to roughly t over n. Yeah, probability of arrival of a customer is basically the size of this window divided by lambda. Yeah, which I believe is t over n. Yes, yes. All right, good. And this is going to be our, this is our p. Okay. So what's the probability of no arrivals? Well, I've got this, yeah, I think in unit time, I think I need to actually make this lambda t. The idea being that if you fix some sort of unit of time, let's say an hour, then this is just going to actually be equal to lambda. So I'm just going to double check. Double check that value actually works out. Anyhow, so let's continue. So the probability of no arrivals in window 0t, we can model as a geometric, where in particular the probability that the first success occurs after the nth window of time, the nth window of time meaning after we're past t, is equal to, well, 1 minus the probability of no arrivals, or a probability of arrivals, so 1 minus that probability is probability of no arrivals, raised to the nth power. So probability of no arrivals equals 1 minus lambda t over n. All right, very good. So consequently, if I do my usual thing, I can say that, all right, well, the probability that there was my first arrival occurred in those first sort of n time steps is just 1 minus this expression, which I can approximate again using my little e approximation. Ends up being e to the minus lambda t. And so then this I can think of as 1 minus e to the minus lambda t. So this sort of accumulates the probability of someone arriving in the first n subdivisions of my window of time, 0 to t. So if you sort of believe me, you can think of the probability that t less than or equal to n as the sort of cumulative distribution of there being at least having an arrival in one of those many time steps, x1 through xn. And so I'm going to think of that as 1 over e to the minus lambda t. Now, one of the common tricks, and this is what I'm going to go ahead and call the CDF trick. And we're going to go over this in sort of simpler examples. Well, the CDF trick essentially says that the derivative, so dd, I'll say t in this case, of the CDF, which say is some function of t, is equal to the PDF at t. Which just essentially expresses this fundamental theorem of calculus, which is that if you differentiate an integral, you get what's inside the integral. And again, the CDF is defined as the integral of what's underneath the curve, right? So this is just basically the fundamental theorem of calculus. If f of t is equal to the integral from minus infinity to t of some PDF, f of x dx, then the f prime of t is actually equal to f of x evaluated at t. This is one of the fundamental theorems of calculus. All right, so this just means I need to differentiate this expression right here. So if I pass this through the CDF trick, I end up getting that the probability that my first arrival happens around time t, the probability of first arrival happens at n times lambda t over n, or sorry, at t over n, which equals t. This can be viewed as the derivative ddt of 1 minus e to the minus lambda t, which ends up equaling lambda e to the minus lambda t. And that is our PDF for the exponential random variable. And notice I was able to kind of get at this continuous PDF by making a discrete approximation and then applying the sort of E estimation for a binomial random variable. So this is the exponential. And so that basically explains in sort of long-winded way where this exponential random variable comes from. So we could take a quick moment to sort of stop and appreciate. Note that I'm not going to sort of test you on this derivation, but I want to at least provide some sort of plausibility for how the people who first thought of this stuff came up with it. Now, one nice thing is that if we look at the number of arrivals within that time window, that is actually well governed by a binomial. So what we just determined was, so let me just back up a little bit here. So I'm going to say no determined probability of basically one arrival in 0t, which is the same thing as asking that this sum equal 1. Well, we might ask, well, suppose I want to know not just when my first customer comes, but like, what's the probability of, say, k customers arriving in this window of time? So how do we determine the probability of k arrivals? So the punchline is that what we're trying to figure out is, all right, probability that Sn equals k, which is a binomial, this can be well approximated using the Poisson. Poisson k, where now lambda is a little different because we want to think of this as being given by the formula n times p. So the parameter now is lambda t, because n times p, this is n times lambda t over n, is lambda t. So this essentially means that we can now think of this as lambda t to the k over k factorial e to the minus lambda t. And so again, you're now starting to see where this exponential random variable came from. Notice that when I put k equals 1, then ideally I want to think of this as sort of unit time, but I get what's important here is I have my lambda and then my e to the minus lambda t. All right, so to be a little more precise, recall that the difference between a binomial random variable with parameters npk and a Poisson with parameters n times p, which again we think of as lambda in general, but in here we have this weird t involved. This is actually bounded by n times p squared. This essentially tells you how good the Poisson approximation is. Now, one of the reasons I bring this up is because if p is equal to this lambda t over n, then we end up getting something like n times lambda t over n squared, which tells us that we have lambda squared t squared over n. So in particular, we can make this approximation arbitrarily good by just subdividing further and further. But I want to show you how this is then all put together and put to use. And I apologize if this feels sort of a little abstract and scattered, and it's going between sort of proofs and applications, but we're kind of blending the two. And the goal behind all this is to understand, again, the Poisson point process applications. This is the kind of question that models, instead of just the first time, you might call it the timeline of, let's say, shark attacks at a beach. Of course, we're worried about when the first shark attack occurs, but if we're trying to predict what the news is going to report, we'll want to also know when's the second and third and things like this. As I already alluded to, this is the kind of thing that models also customer arrivals in a shop. And additionally, phone calls to 911. And just to give you an understanding of where this point comes from, so the point in point process here refers to the point in time of the event. And again, this is trying to further justify why we're talking about a continuous random variable, even though at times we're shifting to a binomial and then also to a Poisson, both of which are discrete. So anyhow, here are the main things we need to use or apply. And I'll think of this as the sort of the main parts of a Poisson point process. All right, so now we get to the application steps. So one is this idea of we need to determine the average rate of arrivals. Per unit time, i.e. when t equals 1. That's being our unit. Like it could be an hour or a day, or a day. It'll be given to you in the problem. This is going to be our lambda. And now what we observe is that that in any interval of time, the number of arrivals in a window A comma B, if I call this is, let me call this NAB, and this is something that's distributed according to a Poisson with parameter lambda times B minus A. Again, here we're assuming that lambda was given in terms of units of time, so we don't need to do this. So it ends up proportional to the length of time. And so that's just we might call this the probability in our first interval. The third observation is that for intervals I1, I2, up through IK, where all these are disjoint. So let's call this disjoint intervals. Each of these n sub I1s, n sub I2, n sub IK are independent random variables. Again, governed using this Poisson random variable. This will be useful because then we can ask about probabilities of arriving, let's say customer arriving right before lunch, the hour after lunch, and things like that. We'll do some examples in class. But I want to conclude by showing what would be the general process for determining, let's say, not the time of arrival for the first person, but now the time of arrival for the second person. So again, the observation here is that this right here, the number of arrivals, is a discrete random variable. Maybe I'll just mention a quick example here. If on average, 5 customers arrive per hour, what's the probability that 2 customers arrive between let's say 10 and 11 a.m. Well, in this case, we're doing 10 and 11 a.m. So this says that I need to do a Poisson where I'm looking for k equals 2, but where the parameter here is lambda times 11 minus 10, which ends up being 1 because I just gave 1 unit of time. So this is then going to be equal to lambda, which is going to be 5. So now it's lambda squared divided by 2 factorial e to the minus lambda. So this is going to be 5 squared 2 factorial e to the minus 5. So that gives you a sort of a taste of how we would apply this process. All right. Last topic for today is I want to go through the derivation of not just the first time of arrival, but let's say second, and then and just tell you the formula for the third or fourth or the rth arrival. All right, so let's go back to the second time of arrival. So we know first time of arrival is exponentially distributed with parameter lambda. So let's try to figure out what is the time of the second one. So let's call this random variable, call this first time of arrival T1. And so we're going to say T1 is exponentially distributed with parameter lambda. Now what about the second? So what about T2? How is it distributed? That's the question we want to try to answer. So again, and this is maybe a more advanced illustration of a concept, which I'm going to make more concrete in next lecture. I want to exemplify this notion of the CDF trick. So it's usually easier first to determine the CDF of this, and then we can actually derive what the PDF is. So let's first think about it this way. What is the probability that the second time of arrival occurs after some time t? So this is the probability that second arrival is after t. Well, this has to be the same thing as the probability of 1 or 0 arrivals in the first time. Can't be 2 arrivals because then that would contradict the event that we're trying to look for, which is that the second arrival happened after time t. So this is the same thing as the probability that there were 1 or 0 arrivals in this window of time, 0 through t. So in other words, to use the notation I introduced on just the previous page, this is the same thing as asking that this number of arrivals random variable, which I'm calling n, in the window 0 to t is less than or equal to 1. And I specified that this function is now distributed as a excuse me, as a Poisson with lambda t as the as that constant as its parameter. So what I need to ask for now is what's the probability that this Poisson random variable equals 0 or equals 1? So this now equals Poisson lambda t of 0 plus Poisson lambda t of 1, which is same thing as e to the minus lambda t plus lambda t e to the minus lambda t. Because again, normally this is to the k, divided by k factorial, but k is 1 in this case. So we've now determined that the probability that the second arrival happens after time t, little t, is this function. So consequently, the probability that t2 occurs before t is 1 minus this. So now by differentiating, so taking d dt, I now get that the probability distribution of t2 is, well, d dt of 1 minus e to the minus lambda t minus lambda t e to the minus lambda t. All right, first thing's easy. The minus lambda comes down and we get our usual lambda times e to the minus lambda t. But now I need to do something else when differentiating this expression, which is t times e to the minus lambda t. So this is an expression where I have to apply the product rule. So I could take the derivative of the first times the second. So if I apply the product rule, this is a derivative of the first times the second, e to the minus lambda t, plus the first times the derivative of the second, which in this case is minus lambda e to the minus lambda t. And so when I combine this all together, I get some, I have a minus lambda here, and then I have to have also a minus and I can see that actually this term is going to cancel. And what I'm left with is now, I guess keeping it in red, it looks something like lambda squared t e to the minus lambda t. Now let me make sure I didn't mess up anything. And yes, so that's right, for t greater than or equal to 0. So this is the PDF for t2. It says that f of t2 of t is equal to lambda squared t e to the minus lambda t. I can just tell you that in general, this leads to something called the gamma distributions. Which you want to think of as the sum of, let's say, in exponentials. More concretely, we can say that the PDF of the nth arrival time is ftn little t of lambda to the n, t to the n minus 1, divided by n minus 1 factorial e to the minus lambda t. And this is for t greater than or equal to 0, and it's 0 otherwise. Zero otherwise. This is the gamma distribution, and it's governed by two parameters in this case, n and lambda. In general, you can actually tune this for continuous values. And so this is just a definition which I offer, and we won't do much with it, but the bulletin for UAlbany requires that I cover this, so I'm going to. So the gamma distribution with parameters r and lambda, and we write this as, so we say x is distributed by gamma r lambda, is the thing which has a PDF that looks like this. So it's f of x, little x, lambda to the r, x to the r minus 1, e to the minus lambda x, divided by, and finally we get to the titular gamma r, which is the generalization of the factorial to all non-negative numbers. X to the r minus 1, e to the minus x, dx is the continuous extension of n minus 1 factorial to non-integer n. All right. So went through a lot. Mostly this is just me doing due diligence. We'll spend, again, class time actually practicing applications of the Poisson point process and looking for arrival times in concrete problems in class, where I look forward to seeing you soon. All right. Until then, bye.